Okay, so here we are with section 8.2, union, intersection, and complements of events, and we've done a little bit of this, I think, in section 8.1, but this is really just taking the the addition principle from section 7.2 and applying it to probabilities. So we'll start with the definition of the addition principle for probabilities and point out how it works for complements. We did some of this in section 8.1, and so we'll talk about probabilities from Venn diagrams. That's problems 1 through 6 and 71 through 74 in section 8.2. A very basic complement problem, that's 25 and 26 in 8.2, and some examples of the addition principle using some of the stuff that we saw from section 8.1. So drawing one card from a deck of cards, that's problems 7 through 18 and 53 through 56. Drawing multiple cards, usually 5 cards, from a deck of cards, so problems 57 and 58, and rolling 2 dice. And then we'll finish with an application of the ideas of these things to quality control. Okay, so a little bit of definitions. So this is the little bit of theory at the beginning. This is the addition principle. So E and F are two sets. Usually if you think about the Venn diagrams, A and B. So E union F, the number of things in E union F is the number of things in E plus the number of things in F minus the number of things in the overlap. So if these are subsets of a sample space S, you can turn this into an addition probability just by dividing everything in sight by the number of things in the sample space. And then this is a probability, right? The probability of E union F is the number of things in E union F divided by the number of things in S. This is the probability of E, this is the probability of F, this is the probability of the intersection of E and F. In terms of just words, right, there's a probability of E or F happening is equal to the probability of E happening plus the probability of F happening minus the probability of E and F happening at the same time. Now when we're dealing with complements, right, the nice thing about if we have some event and it's complement A prime, that means everything that's not in A, remember, then, well, if we apply the addition principle for probabilities, we get probability of A union A or A prime is probability of A plus probability of A prime minus the probability of intersection of A and A prime. But A union A prime, well, that's everything, right? Everything is either in A or not in A, so A union A prime is everything. A intersection A prime, well, that's the empty set. There's nothing that's both in A and not in A at the same time. So what's the probability of A union A prime? Well, it's the probability of S. What's the probability that something happens? Well, that's 1. A intersection A prime, there's nothing there, so the probability of nothing happening is 0. And so what happens in this equation? 1, this is 1 equals the probability of A plus the probability of A prime. So the probability of something happening, or let me rephrase that, the probability of something happening plus the probability of something not happening, well, that's got to be equal to 1, right? Either it happens or doesn't. And that's a useful way to calculate probabilities, as we'll see. So a couple of examples. Here's the first one, a little Venn diagram example. A survey, and of course it wasn't a real survey, I just made these numbers up. A survey interviewed 75 people about their dessert preferences. 38 liked cheesecake, 37 liked chocolate mousse, and 20 didn't like either. So, if you pick a person at random from these 75 people, what's the probability that this person likes both chocolate mousse and cheesecake? And what's the probability that they like cheesecake but not chocolate mousse? So, Venn diagram, we'll start with a little box and 2 circles inside. We label them. This will be our mousse people. This is our cheesecake people. And this is our sample space S. 75 people total that we talked to. And we know that 38 like cheesecake, so there's 38 in this circle, 37 like chocolate mousse, that's 37 in that circle, and 20 didn't like either. Well, not liking either means you're not in this circle, you're not in that circle, so that means you must be outside. So we'll call liking mousse M, liking cheesecake C. So to get a probability, we need to count how many people like, well, this or this or this. So addition principle just for counting. the number of things in M union C, so the number of people who like mousse or cheesecake is the number of people who like mousse plus the number of people who like cheesecake minus the number of people who like both. M intersection C. Okay, so what do we know about all these? Well, we know this is 55. Right? Because there's 75 people total, there's 20 who are not in either circle, so the number of people that are in these three, right, in M union C, that must be 55, 75 minus 20. We know N of M, 37 like chocolate mousse. We know N of C, 38 like cheesecake. And so that allows us to solve for the number of people who like both. Right. Move this over to the other side, move this over to this side. 37 plus 38 minus 55. This is 75. 20. So we can fill out the Venn diagram. 20 in there. If there's 37 people like mousse, there must be 17 here because we already picked up that 20. If there's 38 people who like cheesecake and we got 20 there, then 18 must be there. Excellent. So what are the questions we want to answer? What's the probability someone likes both chocolate mousse and cheesecake? Well, and is the overlap. So if we pick one person at random, probability of getting someone who likes cheesecake and mousse, that is 20 over 75, because that's the number of people who like both, and this is, yeah, who like both, and that's the number of people total. And 20 over 75 is a little over a quarter, 0.2667. Cheesecake but not chocolate mousse. So people like cheesecake but not chocolate mousse, that must be these 18. So probability of people who like cheesecake and not chocolate mousse, so there's our complement. That was 18 over 75. Oops. And that's 0.24. Okay, so calculating from Venn diagrams is pretty straightforward. You just have to figure out how many people you have total, which region you're interested in, and the number in the region divided by the number total. That gives you your probability. Okay, really basic complements here. Right, probability of the rain tomorrow. What's the complement of that? It will not rain tomorrow. So that's the complement. Right? So not, that's the word that gets tied to complements. So if the probability that it will rain tomorrow is 20%, what's the probability that it won't rain tomorrow? Well, obviously 80%, because 100 minus 20 equals 80, right? 100% chance that it will either rain or not rain. 20% chance of raining, so that means 80% chance of it not raining. So complements, I mean, that's how complements work, right? 1 minus the probability of something happening is equal to the probability of it not happening. Often problems involving complements are a little bit trickier than this one. So let's move to some drawing one card from a deck. So problems 7 through 18, 53 through 56. So here's our deck of cards. Suppose one card is drawn at random from a deck of 52 cards. What's the probability that it's a heart? Well, N of S equals 52, our sample space, right? How many possible outcomes are there? There's 52 outcomes because we're drawing one card and it could be any one of the 52. Number of hearts, H is hearts, that's 13. Which one are the hearts? There are 13 hearts, so if you count those. So probability of getting a heart, 13 over 52. And that is 0.25. Not surprising, right? There's 4 suits, right? What's the probability of picking a card from one of the 4 suits? That's 1 in 4, 20.25. What's the probability it's a numbered card? So we'll say n of capital N for numbered card. How many numbered cards are there? Well, these are the numbered cards. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So each suit has 10 of them. So there's a total of 40 numbered cards. So the probability of drawing a number card is 40 over 52. And that is 0.7692. Right. What's the probability that's a heart and a number card? So probability of heart and number card. Remember that and is the intersection. So how many hearts are also number card, or how many number cards are also hearts? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 cards that are both hearts and number cards. And so 10 out of 52 is 0.1923, apparently, if I can read my notes. Great, so far we've just been counting various things, right? And so what we have is these are my 13 hearts. These are my 40 numbered cards. The overlap, that's these, right? That's my intersection of hearts and number cards, right? You can think of the green thing as being the Venn diagram, right? And we have one circle here for numbered cards and one circle here for hearts. So what's the probability if I pick one card at random that I get either a heart or a numbered card? Well, there's a couple ways to do that. We can just count all the cards that are either hearts or numbered cards, or we can say, well, that's going to be the probability of getting a heart plus the probability of getting a numbered card minus the probability of getting a heart and a number card. Right? And so probability of getting a heart we calculated is 0.25. Probability of getting a number card 0.7692 minus the probability of getting a heart and a number card, that's 0.1923. If you add that all up, you get 0.8269. You can also do a direct count of that, of course, right? How many cards are either numbered cards or hearts? Well, here's 40 numbered cards. That includes these hearts. And then there's 3 more hearts to account for. So the number of cards that are hearts and number cards is 43. So from a direct count we can say the probability of getting a heart or a number card is 43 out of 52, and hopefully to nobody's surprise, that's 0.8269. So union, that corresponds to or, so probability of getting heart or number card is probability of heart plus probability of number card minus the probability of getting heart and a number card, a card that's both a heart and a number card. That's what the intersection is. And lastly, what's the probability of getting a card that's not a heart and not a number card? Well, which cards are not hearts and not number cards? Well, clubs, diamonds, and spades, those are cards that are not hearts, right? So we're looking at these cards. Not numbered cards, well, these are all numbered cards, so we don't want to look at that. So it's just these and those. These 9 cards are the cards that are not hearts and not numbered cards, right? And so there's 9 of them. So probability of a card that's not a heart, so complement of hearts, and not a numbered card, right? So prime complement is not a numbered card. That's 9 out of 52. And that's 0.1731. Note that this and this are complements, right? These two add up to 1. Getting a card that's either a heart or a number card has as its complement getting a card that's not a heart and not a number card. That's the 0.1731. Okay. Drawing multiple cards. So, suppose 5 cards are drawn at random from a standard deck of 52 cards. What's the probability that at least one face card is drawn? At least. This is something that actually is one of the words that's a tip-off that we're dealing with a complement problem. So I'm going to draw a little picture. A Venn diagram-ish kind of picture. This is our sample space. It's all 5 card hands. All 5 card hands. And how many 5 card hands are there? Well, we're choosing 5 cards from 52. Okay, so that's how many possibilities there are. If we think about that we get at least one face card, well, if you think about picking 5 cards at random, how many face cards can you get? Well, you can get 0 face cards, right? F for face card. You could get 1 face card. You could get 2 face cards, or you could get 3 face cards, or you could get 4 face cards, or you could get 5 face cards. Right? So, if you're drawing 5 cards at random from a standard deck of 52 cards, you either get no face cards, 1, 2, 3, 4, 5 face cards. Now, what this question is asking is, what's the probability that you get at least 1? And so how many is at least 1? Well, that could be 1 face card, or it could be 2 face cards, or 3, or 4, or 5 face cards. So we want this set that's in red. What's the complement to the set that's in red, right? If this is the entire space, the entire sample space, and this is the red subset, what's the complement? Well, 0 face cards. So go back to a black pen. If we set E is the event of drawing at least 1 face card, then E prime is drawing 0 face cards. And why would we want to be interested in drawing 0 face cards? Well, figuring out the probability of E prime is much easier than figuring out the probability of E. To figure out the probability of E, you have to figure out the probability for each one of these 5 things, and it's a little tedious. But I can figure out the probability of drawing no face cards pretty easily. How many hands have no face cards in them? Well, I need to pick 5 cards out of 40. And, oops, I'm just doing the count, so I don't need the denominator yet. C of 45, right? Why 5? Because it's 5 cards that I'm picking. Why 40? The 40 cards that are the numbered cards that are not face cards, right? So we're drawing 5 cards from 40 not face cards. So that's the number of way to pick the number of possible 5 card hands that have no face cards in them. So the probability then of drawing no face cards is C 40, 5 over C 52, 5. And what is that? 0.2532. Great. So what's the probability of drawing at least 1 face card? Well, that's 1 minus the probability of drawing no face cards. 1 minus 0.2532, which is 0.745. 6, 8. So about a quarter of all hands have no face cards. About 3/4 of all hands have at least one face card. Okay, rolling 2 dice. This is also a complement problem, right? Because things like at most or at least, right, those are all usually tip-offs that we're dealing with a complement problem. So again, if we think about drawing a little Venn diagram here, well, not a Venn diagram, it's supposed to be a table, but we'll just leave that out. There's a table for the number of probabilities of the number of possible outcomes here. Unfortunately, I didn't prepare it and I don't really want to draw it out, so we'll just say there are 36 possible outcomes. Right? How many of them give me a sum at most 10? So that would be getting a 2 or 3 or 4 or 5 or 6, 7 or 8, a 9 or a 10. What's the complement of that? Well, that's rolling either 11 or a 12, right? So if that's rolling in either 11 or 12, how many ways are there to roll an 11 or a 12? There's 3 ways to do that. You can roll a pair of 6s, that'll give you 12, a 6 on the first die and a 5 on the second die, that would give you 11, or a 5 on the first die and a 6 on the second die, that would give you 11. So what's the probability of rolling an 11 or a 12? 3 over 36. So what's the probability of rolling at most 10? Well, that's 1 minus 3 over 36, which is 33 over 36, which is about 0.9167. About a little more than 90% of the time you will roll a number that's at most 10. You won't get an 11 or 12. This is, what's that, 0.0833. 8% of the time you roll an 11 or 12. So complements are useful. They can shortcut the time it takes to calculate a lot of things. Usually if you see at most or at least, that's a tip-off that you might be dealing with a complement problem. Finally, how do you actually see some of this stuff in real world? Well, a lot of quality control processes are based upon this idea. So suppose we have 120 tablets that are shipped to a retail store and 14 of the 120 are broken. And so the store, they do a quality control check. Do we want to accept this shipment or not? Is it just too broken? So they select 10 of the 120 at random, and then they examine those 10. If at least one of them is broken, then they ship back the entire shipment and just say, this is just too many were broken. So what's the probability that it returns if 14 of the original were broken? So what's the sample space? They're selecting 10 at random out of 120. So it's like the problem with the cards, right? When you're dealing a deck of cards, you pick 5 out of 52. Here we pick 10 out of 120. How many ways are there to pick 10 out of 120? See 120 come in 10, which is a very large number, actually. Of all these shipments, then not of all these shipments, of all these choices of 10, how many have at least one broken one? Well, that's hard to answer, but the complement is actually pretty easy to answer. What's the complement? How many choices of 10 have 0 broken tablets. Well, if we pick 10 unbroken tablets, there's 120 minus 14 equals 106 unbroken tablets. So the probability of picking 10, not the probability, but the number of ways to pick 10 unbroken tablets is C 106, 10. So that's how many choices of 10 consist entirely of unbroken tablets. Great. So what's the probability of getting an unbroken tablet? Of getting 10 unbroken tablets, sorry. Well, it's the number of ways to pick 10, C106, 10, over the total number of ways to pick 10 out of the entire shipment of 120. And that is, where did I write that down? Oh, here it is. So that's 0.2744. That's the probability actually that they keep the shipment. The probability that they don't keep the shipment is the probability of at least one is broken. But by the magic of complements, we know that's 1 minus the probability that you chose 10 that are unbroken equals 1 minus 0.2744 equals 0.7256. 72.5% chance that they ship it back. So complements are very useful in figuring out probabilities, because this would be a very hard thing to do if you didn't use the complement. In an actual example in real life, of course, you don't know how many are actually broken. There are ways to get around that. There are ways to estimate that. But this is a basic idea behind a lot of quality control. You sample stuff that's coming off the factory line, for example. Sample every 10th one, and if the failure rate in the sample gets too high, then you shut down the line and fix it and see what's going on. Okay,